this chapter, we will examine the effects of external forces on the behavior of materials and test methods to assess basically the behavior of materials. And we will look at mechanical properties such as elastic modulus, yield strength, ductility, toughness, and the tests that are applied to measure the mechanical properties such as tension, compression, bending, hardness, and fatigue. And finally, we will end this chapter with a description of types of and factors involved in failure and fracture of materials. So, in manufacturing operations, parts and components, they are formed into a variety of shapes by applying forces to the workpiece, and usually the forces are applied by tools and dies. And here in the table we are seeing relative mechanical properties of various materials at room temperature at a decreasing order. So if we look at the strength, most strong materials are usually fibers, glass fiber, carbon fiber, Kevlar fibers. Hardness, diamond is the hardest material known. Toughness, ductile metals are tough. And stiffness, the most stiff materials are diamond, carbide, tungsten. This is because of strong covalent bonding. Okay, and strength per density means we call it also specific strength. And of course, the first one is reinforced plastics, the composites, right? Because they are lightweight due to use of plastics, and strong because reinforcing with the fibers. Okay. Tension test is the most common technique we use to determine mechanical properties of materials, such as strength, ductility, toughness, elastic modulus, and strain hardening exponent. So, how do we do this test? The first thing is we prepare a test specimen. Okay, and it is here seen. And this is before we put it in the machine and start pulling. And after pulling, it's gonna look like this, right? So the specimen is then mounted in the jaws of the testing machine. An important thing here you guys need to remember in tensile test, we keep the deformation rate constant. That means, for example, for every second we deform it 5 centimeters. Let's say, I'm just making it up to make you understand. Okay, so the deformation rate is gonna be constant no matter what throughout the experiment. Okay, throughout the test. So what the machine measures then? It measures the change in the length with the applied stress and records it. Okay, so a typical test result is shown. So this is the initial length, L0 is the original gauge length, initial length of the specimen, and this is the final length of the specimen before it breaks basically. Okay, so the typical test is gonna look like this, typical test result. Initially, when the first load is applied, the specimen will show a behavior we call linear elastic, meaning this region, linear region. So in this region, if we remove the forces, the specimen can return back to its original length. Okay, and since the specimen elongates in proportion to the load, there is a proportionality constant given also by the slope in that region, right? This one. given by the slope, which is the elastic modulus or Young's modulus or modulus of elasticity, and it is defined by Hooke's law. Okay, so the relation between stress, applied stress, and the strain is given by elastic modulus. Okay, so after this, after we reach when we reach the yield strength, this is where we are shown with Y, the yield strength. This is after this, the permanent or plastic deformation occurs once we reach this yield strength. Okay. So usually for soft and ductile materials, it is not an easy determination to change from this linear region to non-linear region. So it is not easy to determine the yield strength. So for such materials, usually the yield strength is determined by drawing a line with the same slope as the linear curve as shown here. Okay. And then, but it has an offset by a strain of 0.2%. 0.2% elongation offset. And we start drawing the linear line that is parallel to the elastic region. Okay, and then where it intersects the curve right there, we go to the y-axis and read the yield strength. Okay, you can see throughout the experiment how the specimen looks like. Right, this is once we reach the elastic region. At the end of elastic region, we reach the yield strength, and then this is where we reach the ultimate tensile strength. Okay, and of course after this part, you guys know the necking forms. Cross-sectional area starts to decrease. And after that, we go to fracture strain and fracture length and the fracture area, where basically the sample goes through fracture and fails. Okay, so besides that, there is also another important property. We call it Poisson's ratio. Because the elongation of specimen under tension is accompanied by lateral contraction, the absolute value of the ratio of the lateral strain to the longitudinal strain is known as Poisson's ratio. And do you guys know which material has a Poisson's ratio of 0? It is cork. Cork has 0 Poisson's ratio, meaning there is little lateral expansion when compressed. Okay, so to continue, as we increase the load, okay, the engineering stress reaches a maximum, I told you guys, and this is called the ultimate tensile strength, or it is also called tensile strength. Both of them are describing the same thing. Okay, so what are the equations? How the engineering stress is defined? Because you know the device only records the force that needs to be applied to keep the deformation rate constant. Okay, so and then measures the deformation. That's it. So it needs to convert this force to the stress. So how does it do it? The engineering stress is defined by force over cross-sectional area, but original cross-sectional area. So throughout the experiment, it only changes the force that needs to keep the deformation rate constant and keep dividing it to the original cross-sectional area, not changing the area, and always calculating from that equation the stress and drawing the curve. So what about the deformation or strain? Strain is measured by engineering strain, right? So it is length, instantaneous length, minus original length over original length. Okay, so this is engineering strain. So once we reach this ultimate tensile strength, the necking begins. Necking is, that means the cross-sectional area of the specimen is no longer uniform along the length, and it is getting smaller in the necked region. So that means actually the force, so since it is getting smaller, right, during the necking, like this, right? Since it is getting smaller, the device now has to apply less force to keep the deformation rate constant. So the force is decreased, but the cross-sectional area stays the same in the equation. Okay, then therefore the stress is decreasing. Therefore, that's why you are observing this decrease in the stress. Okay, so after that the engineering stress drops, and at some point the specimen cannot handle the forces anymore, and it fractures at the necked region. So this point is known as the breaking or fracture strength. Of course, if the specimen is unloaded over a stress value that is higher than the yield stress, what happens here is the curve follows a straight line parallel to the original one and downward. Okay, unloading. That means because after the yield stress, the permanent deformation started, you can still recover the elastic deformation part, but there is gonna be a permanent deformation remain in the sample, this much. Okay, this much will be remain in the sample. So what about ductility? What is ductility? It is how much we can deform the material before it fractures, and there are two ways to measure ductility. One is the total elongation of the specimen, the other one is reduction of area given by these equations. So in the elongation we have final length minus the original length over the original length times 100. And if we measure the percent reduction in the area, original area minus final area over the original area times 100. So what we have just learned was an engineering stress-strain curve. There is also true stress-strain curve. It is obtained similarly, but this time the force is not divided by the original cross-sectional area, but instead it is divided by the instantaneous cross-sectional area. Therefore it is not decreasing after the necking as we observed in the engineering stress-strain curve. In this case it will be decreasing, okay, because since this is decreasing and the force is decreasing at the same time, they are not decreasing at the same in the same amount. Therefore it actually area decreases to a larger extent, keeping the stress increased instead of we observe in the engineering, right? Engineering stress-strain curve is like this. After this point it decreases, okay, because the force is decreasing, but we are dividing it to the original cross-sectional area. So it is decreasing. In the true one, it is always increasing like this. This is the true stress strain curve. And then the true strain is the logarithm or logarithmic ratio of the current instantaneous length to the original length. So in this table we are seeing mechanical properties of various materials at room temperature. Say aluminum alloys, copper, lead, all metals in this table, and in the next table there are other materials also, glass, fibers and polymers, ceramics. Here we are seeing elastic modulus ranges and yield strength, ultimate tensile strength, elongation in 50 millimeter means percent elongation ductility. 50 millimeter means generally the original gauge length is the original length of the specimen is 50 millimeter. So it is giving you the original length 50 millimeter, and then the Poisson's ratio of the materials that you can compare. Okay. So as I told you guys, what the device measures, always remember it keeping the deformation rate constant, and it is to do that it is measuring the force that it needs to apply and also measuring the extension, the change in the length, and it is recording it like this. Okay, and then after this data is obtained by the equations we learned, the stress equation and strain equation, by their definition, it is calculating the stress strain curve, and it is looking like this. This one is engineering stress strain curve. And this one, on the other hand, the C, okay, this is the true stress strain curve. Okay, and since in this case we are not dividing to the original cross-sectional area, it keeps decreasing like that. So true stress strain curve actually given by this equation here. K is a strength coefficient, N is the strain hardening or work hardening exponent. The slope of the curve is N, the strain hardening component. This is the strain, this is the N, strain hardening exponent or work hardening exponent. K is a coefficient, and this is how stress and strain are related, and it is explained by this equation. Okay, and then of course the higher the slope, the greater the N. That means the greater the strain hardening capacity of metal, meaning the stronger and the harder it becomes as it deforms. So we know that when we deform the material, it gets stronger, right? And this is called strain hardening. As you work on the sample, as you keep deforming the sample, you increasing the strength. We learned that. And of course, this strain hardening exponent is giving us information about the strain hardening capacity of the material. And if it's bigger, if the slope is higher, that means N is bigger, right? If N is bigger, that means it will get more stronger and harder as it deforms. Okay. In this table, we are seeing basically the values of K and N for some metals. And you can see that annealed copper and brass and stainless steel, they have high end values. This means they can be stretched uniformly to a greater extent than the other metals that are listed in the table. So here we seeing again the true stress strain curves for variety of metals, and we need to be careful here because the curves are starting at the yield stress of the materials here for all materials here, and we can see how the different materials behave differently. For example, steel, aluminum, copper, they are all located in different regions in the chart. That means they are showing different behaviors. Even the heat treatment changes properties. For example, for the same brass, if you anneal means heat treat, you can see how the slope is changing, and it is also showing better strength values when you look at the stress strain diagram. The area under the true stress strain is known as the material's toughness. By definition, it is the amount of energy per unit volume that material dissipates prior to fracture. So this property is very important, especially if you want your material to absorb a lot of energy before it can fail, such as maybe you are going to select materials for a car bumper, right? And you want your material to maximize the energy absorption before it fails. So therefore, toughness is an important property in that sense. So necking, why necking occurs? So as we strain the material, we know that it gets stronger due to strain hardening, but also the cross-sectional area is becoming smaller, actually at a higher rate. So we talked about necking, that necking actually starts at the ultimate tensile strength. The true strain at the onset of necking is numerically equal to the strain hardening exponent n. So that means the higher the value of n, the higher the strain that a material can experience before it begins to neck. And why this information is important? Because in many of the manufacturing operations, the workpiece will be stretched, right? And of course, when we are stretching the material, we don't want it to experience necking. So we need to choose materials for higher end values wherever the workpiece has to be stretched. What about the effects of temperature on stress strain curve? It has two effects. The ductility and toughness increase. Ductility, of course, percent elongation, and toughness increase. Yield strength and tensile strength, those decrease, and elastic modulus also decrease when we increase the temperature. Okay. Temperature has also a major influence on the strain hardening exponent n, and it increases with increasing temperature. Materials in manufacturing operations, of course, can be shaped at different speeds. So it is important to understand certain definitions. What is deformation rate? What is strain rate? Deformation rate is the speed at which the specimen is stretched. And I told you guys during the tensile test, deformation rate is kept constant. But the strain rate is a function of the specimen's original length. So what do we mean? Assume you have two rubber bands. One is 20 millimeter and one is 100 millimeter. And they are stretched by 10 millimeter per second. So actually both have the same deformation rate. Both are stretched 10 millimeter per second. But what about the strain rate? Do they have the same strain rate? We know the strain is 10 over 20 for the first one. And for the second one, second rubber band, it is 10 over 100.1. So that means the short one is being stretched at a strain rate that is 5 times higher than that is for the long one, right? So 0.5 per second, 0.1 per second, that is the strain rate. And some typical ranges of strain and deformation rates that we use in manufacturing processes are given in this table. And as you can see, we encounter wide ranges of deformation and strain rates in practices. Let's see the effects of strain rate on the tensile strength for aluminum. So if we look at this chart here, for the same temperature, let's look at this one, okay? For the same temperature, as we increase the strain rate, the strength of the material increases. So this is the strain rate hardening, okay? As we keep increasing the strain rate, the material gets stronger. So this is called strain rate hardening. And the slope here in this curve, the slope is M. M is the strain rate sensitivity exponent. How strength changes with the strain rate is given through this equation. So this is strength, this is strain rate. M is the strain rate hardening, the strain rate sensitivity exponent, and C is the strength coefficient. We also see the effect of temperature here. As the temperature increases, we see that slope, right? As we increase the temperature, the slope is increasing. So that means since the slope is M is increasing. So this means strength becomes more and more sensitive to the strain rate as the temperature is increasing. So M increases with increasing temperature. If you look at here, actually this one, right? This is relatively flat at room temperature. That means the M is very low. So typically M is 0.05 for cold working. Okay, in the background I'm sorry you hear noises. And then this goes up to 0.4 for hot working. Alright, so in many manufacturing technique, the workpiece is subjected to compressive forces. And how do we measure the effect of compressive forces on the material is through doing compression tests. And basically compression test is where we subject the specimen to compressive forces. So you have two flat dies and applying forces, you are compressing your test material here. Okay. Of course, there are friction in between the specimen and the dies in this region. Friction. Due to this friction, specimen cannot flow freely in these regions. That causes the specimen to bulge. Right, as you push it, it will bulge like this, and you can see it in this image. So initially this was the specimen. As they press on it, it starts to bulge, and this is called barreling here. Okay, because of this, basically along the height, the cross-sectional area will not be the same. It's gonna vary. So the equations we use to calculate, since they are using area, it is gonna not giving us accurate information. Plus, to overcome this friction we talked about over here, we need to apply extra force. So even those will not be representing the real forces the material experiencing. Therefore, usually compression tests are not very reliable. So there is this effect, Bochinger effect. So this is when we first subject the specimen to tension and we deform it plastically, and then when we release the forces, now we apply compressive load. The yield strength in compression is found to be lower than that is in tension, and this phenomena is explained, is defined as Bochinger effect. So basically this is explained through the motion of dislocations again. So basically when we apply tension, dislocations accumulate in the grain boundaries, pile-ups and tangles. But when we apply compression, which is a stress in reverse directions, now the dislocation move back to their positions, and material will not be as strong as the previous case. So this is also called strain softening or work softening. And for brittle materials such as ceramics and glasses, usually disc test is used. And in this disc test, the material is subjected to compressive forces, and the specimen is loaded as shown in the image. And when it's loaded like that, tensile stresses are developed that are perpendicular to the vertical center line along the disc. Therefore, it causes crack to propagate along these directions, right? So basically fracture is initiated, disc, and then splits into half. And the tensile stress that is induced basically can be calculated through this formula given here. P is the load, D is the diameter of the disc, and T is the thickness. Of course, not only tension and compression is important, because during manufacturing, many of the work pieces will be subjected to shear stresses. And how do we determine the reaction of a material to the shear stresses, basically? And usually we determine this with a torsion test. And many of these you have learned in mechanics of solids. So in the torsion test, we have a specimen and we mount it in between two heads of a testing machine and we twist it. And the shear stress can be calculated through this formula here given. T is the torque, R is the average radius of the tube, and T is the thickness of the tube at its narrow section. And shear strength can be calculated through this equation here. R again the same, and L is the length of the tube section as shown in the figure, and phi is the angle of twist in radians. So the ratio of shear stress to shear strain in the elastic region, just like the Hooke's law in this case, is giving us the shear modulus of elasticity, G. And the elastic modulus, Young's modulus, related to the shear modulus through this equation with the use of Poisson's ratio. So the angle of twist, it is important in manufacturing. It gives us information about the forgeability of metals. So the greater the number of twists prior to failure, the better the forgeability. Testing brittle materials, it is very challenging. And the reason for that is it is difficult to shape them, machine them to appropriate specimen dimensions. Also, they are very sensitive to cracks, and therefore clamping them to test devices, it's very difficult. So therefore other tests are being utilized to calculate their properties. One of them is bend or flexure test. Basically it involves a specimen that has a rectangular cross section and supported in the manners shown. Tests are known as 3-point bending test, 4-point bending test, and the stress at fracture is known as modulus of rupture, transfer rupture strength. So what is hardness and hardness test? How do we measure the hardness? Hardness is known as the resistance to permanent indentation, and it is very directly related to the strength of the material. And several test techniques have been developed to calculate, measure the hardness values of materials. And the most common ones, they are given here, like Vickers hardness test, Rockwell hardness, and durometer, leap test. So the leap is usually it's a portable device testing large work pieces, and durometer is usually a technique that is measuring hardness of rubbers, plastics, soft and elastic non-metallic materials. So here you see in the figure and general characteristics of hardness testing techniques and the formulas for calculating the hardness. So the most common one we are familiar with here, Brinell hardness test. For example, it involves an indenter, which is either steel or tungsten carbide, and the shape of the indentation is given, side view and top view, typical loads that are applied during the test, and how the hardness is related to these dimensions of indentation and the force that is applied. So similar to that, all other techniques are listed: Vickers, Knoop, and rock wall hardness tests, and what type of indenter they are using, what is the shape of the indentation, typical loading that is given, and also how hardness is related to the force and the dimensions of that indentation. So depending on the surface condition of the material tested, two types of impressions can develop. If it is an annealed metal, usually the impression is a rounded profile around its periphery. And in cold work metals, it is like sharp profile. And you can see that hardness itself is actually related to the strength. So how it's related to the strength? And for the yield strength, if we look at the yield strength, 3 times of the yield strength is the hardness value for the Brinell hardness. So 3.5 times the Brinell hardness number is the ultimate tensile strength. So this is how they related to each other. So hardness number itself has no meaning, but how it relates to the strength is important, so we can establish a relationship between the hardness and strength. So many times it is easier for us to calculate the strength through hardness testing, because the hardness test is very simple, not like you don't have to do all the tensile test, right? It is easier to do hardness tests and calculate the stress and strength from there. And in this figure, we are given different types of hardness tests and how the result hardness numbers are related to each other. So if you need to do any conversion in between different hardness values. So what is fatigue? Many components in manufacturing, they are subjected to cycling loads. The tools, die, shafts. What is cycling load? Like the part will be under tension, compression, loading cycles. And under these conditions, material usually fail, even if the stresses that it is exposed to is lower than its failure strength. This is because with the fatigue, with the cycling loads, a crack can form with each cycle and grow. So each cycle means one cycle is one cycle of tension and compression. Okay, so this is known as fatigue failure. Once the crack forms and grows, and with each cycle, and the material fails at some point. So this is very important. Fatigue failure is responsible for the failure in many mechanical components. How do we do the fatigue test? So at certain stress amplitudes, the number of cycles n to cause the total failure of the part is recorded. So what does the stress amplitude is? Remember, one cycle is tension, compression. So what is the stress during the tension? What is the stress during the compression, right? So the stress amplitude, if you think about it like tension, compression, and here it's the stress. This is the stress amplitude. Okay, so for each stress amplitude, basically they are measuring number of cycles to cause the failure. So each cycle is one here. Here, let me change the color. So one cycle is one cycle of tension and compression. This is one cycle. And for each stress amplitude. Let's say if you look at the chart here, at 400 stress amplitude, 400 megapascal, they measured how many cycles necessary for the part to fail. So it's 10 to the power of 5. So first they determine the first point, and then they lower the stress, let's say to here, and then they figure out this is the number of cycles to failure. And when you reach a certain value, so this is how they record SN curves to get information about the fatigue failure. But at certain point, at certain stress amplitude, let's say for steel, when we reach 300, when the stress applied is 300, there will be no more failure with fatigue. And this stress is called endurance limit. So at 300 and below, the stress is below that, the material will not fail with fatigue, and this is the endurance or fatigue limit. And we are seeing in this SN chart that we have a steel and aluminum alloy, and steel has an endurance limit, but the aluminum alloy does not have an endurance limit. So some metals might not have an endurance limit like aluminum, okay, and it has a downward trend like this. And on the right we are seeing an SN curve for common polymers. So the endurance limit for metals can be approximately related to their ultimate tensile strength. So in the y-axis we are seeing endurance limit per tensile strength. And for carbon steels, for example, if you look at that, this ratio is 0.5. So that means the endurance limit is 0.45 times of the tensile strength. So creep, what is creep? Creep is the permanent elongation of a material under a static load maintained for a period of time. It is a slow, continuous deformation with time ending in fracture. One example, everyday life, is tungsten filament that sags over time under its own weight, and the turns of the coil touch each other and the lamp burns out. This is how your lamps burn out, because over time, under its own weight, it goes through creep, because there is high temperatures over there, right? It is especially important in high temperature applications, therefore, like gas turbine blades. The mechanism of creep at elevated temperatures, we talked about that. It is with grain boundary sliding. And in the creep test, and the specimen is subjected to a constant tensile load at elevated temperatures. And what we measure the change in length at various time increments and record that. So with time, we measure the strain, okay, at a constant loading. So this creep curve consists of 3 regions: primary, secondary, and tertiary stages. Okay, so during the test, the specimen eventually fails by necking and fracture. This is called rupture or creep rupture. And as expected, the creep rate increases with the specimen temperatures and the applied load. And the most important part here is, this part is giving the slope. This is more linear, and the slope is gonna give you the creep rate. Creep rate. So again, during manufacturing operations, materials are subjected to impact and or dynamic loading. And a typical impact test is done when we place a notched specimen in an impact tester and breaking it with a swinging pendulum. Of course, the pendulum has initially certain potential energy, and here is your notched specimen. And basically, after the pendulum hits the specimen will absorb during its breakage will absorb some part of that pendulum, and when it goes to the other side it will not raise to the same starting position because it lost its potential energy. The specimen absorbed its energy. So this is very important because we are measuring the sensitivity of materials to surface defects. Right, our specimen has a notch, and so there are two types here, Izot and Charpy tests, and the difference here is how the specimen is supported. In one of them the specimen is just supported at one end. Here it is supported at two ends. And if you're interested how this test is done, you can actually watch this video given to you. So when we look at the failures in materials, two types of failure. One is fracture, either internal or external cracking. And fracture is also subclassified into two categories, ductile fracture or brittle fracture. And the second type of failure is buckling. So in A, we are seeing ductile material fracture. First the necking and then the fracture of the material. B is showing us buckling, failure by buckling under compressive loads. And C is fracture of brittle materials under compression. And D is again cracking under compression. Remember, when you apply forces like that, tension happens in that direction, and this causes cracking of the barreled surface in the ductile materials in compression. So we've said the fracture is happening is ductile and brittle fracture, and it is important to understand the fracture morphology because it gives us idea about the behavior of material. And ductile fracture is usually characterized by plastic deformation before it actually fails. So in A, we are seeing no plastic deformation, so therefore it is a brittle fracture in polycrystalline metals. And this one is in a single crystal shear fracture. So we can understand there is some directionality to the fracture. Therefore, it is usually happens in single crystals because some 45-degree angle, the materials are experiencing the maximum shear stresses. That's where the fracture happens. And C, most metals and alloys experience first necking, as you can see here, before they fail. And this is actually called cup and cone fracture in ductile materials, the cup and the cone fracture. Okay, so it looks like that. And D is complete ductile fracture in polycrystalline materials. As you can see, 100% reduction in the area. This is usually materials like gold, lead, where they are highly ductile materials, they can experience a point before they actually fail. So this is how ductile fracture surface looks like under microscope, is showing dimples. And usually for formation of these voids, basically dimples, is a result of the presence of inclusions, impurities or voids. And you can also see sometimes within the depth of this dimple the inclusion or impurity. So failure is initiated with the formation of tiny voids, and usually this is happening around small inclusions or pre-existing voids, which then grow and coalesce and develop micro cracks, then to continue to grow in size and then lead to fracture. And if we examine closely the surface of ductile fracture, we see a fibrous pattern with dimples. And fracture begins at the center of the neck region, right there, right? And crack then propagates and results in the failure. And as you can also see, we are seeing the cup and cone fracture here also. So, because the nucleation sites for voids have inclusions. And what are inclusions? The inclusions are usually oxides, carbides, sulfides that are already in the structure. And these are responsible for the formation of voids, right? So these are very important in the manufacturing, because they can be the reasons why we have defects, or they can be the reasons why the material fails during manufacturing. Okay. And the extent of their influence will depend on factors such as their shape, hardness, distribution, and the greater the amount of the inclusions, of course, the lower the ductility will be. And during the manufacturing, because of these inclusions, voids and porosities can form in the metals. So two things are very important. First, what are the factors that are controlling the void formation, basically? One thing is the strength of the bond at the interface between the inclusion and the matrix. Okay, so if this bond is strong, then there is a lower tendency for void formation during deformation. And of course, hardness of the inclusion is very effective. If it's a soft inclusion, manganese sulfide is a soft inclusion, for example, it will conform to the overall shape and during the plastic deformation. If it's a hard inclusion, however, such as those are carbides and oxides, it's like a ceramic material, right? Carbides and oxides, and those hard inclusions can lead to void formation during the manufacturing. Okay, so along this direction they are strong, but along this direction they are weak. The reason is because the crack can propagate when the stresses are applied along that direction. Okay, So the alignment of inclusions during plastic formation leads to mechanical fibering. So during the deformation, of course, the inclusions will align, and of course this will create an anisotropy. Remember, the properties will depend on the direction. So a type of anisotropy that results from the alignment of inclusions is called mechanical fibering. So there is this temperature which is very important. It's called ductile to brittle transition temperature. So this temperature, transition temperature, below that materials will behave as ductile materials. Of course, this is for some metals, okay? So for some metals, below the transition temperature, the materials behave brittle. But above that, materials behave, because their ductility increases, you can see. Above the transition temperature, ductile to brittle transition temperature, they are behaving brittle, like ductile materials. So this is why Titanic actually failed, because they were going in very cold temperatures, and normally the ductile steel they made all the ship from, right? Normally the ductile steel, when under cold temperatures, it became brittle, and when they hit the iceberg, pretty much the material, since it's a brittle material, it's acting as a brittle material, it cracked and the Titanic sank. So that's why this is important. This is also the reason why Challenger space shuttle disaster happened, because they were using rubber seal, and rubber during the day of the launch, it was very cold, like -4. They didn't take into account how the temperature will affect the material, so it didn't seal, because the rubber acted as, normally the very ductile rubber acted as a brittle material. It didn't do its job as sealing. So that's why the disaster happened. So this temperature is very important. Okay, so sometimes there is this phenomena, strain aging, that we need to learn about, and this is where carbon atoms affect the dislocation motion. So sometimes the carbon atoms can get together in the structure and prevent dislocations from moving. Remember, this is how the materials change shape, and if we stop dislocation motion, we increase the strength of the material. So this is called strain aging. And one type is blue brittleness. Of course, when we increase the strength, we are making the material brittle, because since the dislocations cannot move, material cannot change shape. And the reason it is called blue brittleness is because when the temperature is exposed to heat, there is going to be a bluish oxide film that develops over steel. That's why it's called blue brittleness. And the heat is responsible for these carbon atoms to segregate at the first place. So we learned ductile fracture. What about brittle fracture? Of course, brittle fracture doesn't happen with plastic deformation. Either it is very little or not at all. So usually brittle fracture does not happen with FCC metals. This is because of their packing and the number of slip systems. Brittle fracture is more common for BCC and HCP metals. And in general, low temperature and a high rate of deformation promote brittle fracture. And most common path observed is transgranular, meaning through the grains. So we are seeing here in this image, microscopic image, a brittle fracture that is happening through the grains. So there is also intergranular fracture. In this case, the crack propagates along grain boundaries. Okay, and it generally occurs when the grain boundaries are soft and contain a brittle phase, or they have been weakened by liquid or solid metal embrittlement. Fatigue failure generally occurs in a brittle manner. Remember, fatigue failure is associated with cyclic loads. And as you can see in this microscopic image, the surface in fatigue fracture is generally characterized by the term beach mark because of these appearances. So this is how people look at the fractured surface and get information about why the material actually failed. And if we see these beach marks, we can conclude that the material is actually failed by fatigue fracture. So how can we improve the fatigue strength? There are certain techniques. First one is to compensate the tension, to compensate against tension. We can introduce compressive stresses on the surface with certain techniques we're gonna see. Or we can do case hardening. This is basically increasing the strength of the surface with different techniques. Or producing a fine finish. This is because if we have imperfections, scratches, notches on the surface, it has effects of propagating and getting into a bigger crack. Therefore, we can have a very fine finish on the surface, and this will provide us a better fatigue strength. Or we can select materials such as they don't have inclusion voids or impurities that can act as places where the voids can form into cracks, and then cracks can propagate and the material can fail. So here we said the surface finish is important. And now we have a chart how it shows us the effects in the fatigue strength by how it is affected by different surface finishing operations. Of course, fine polishing compared to as cast will give us the more smoother surface, right? Better surface finish. That's why we are seeing it doesn't have any reduction, causing any reduction in the fatigue strength. So how actually the fatigue strength is reduced in the materials? If there are tensile residual stresses on the surface, this affects the fatigue strength. Decarburization, meaning surface degradation happening, such as during the forging or heat treatment of steels, the carbon. We are losing carbon from the surface. So this can create not a very good quality surface. So this can cause fatigue cracks to propagate and form. When surface pits, usually due to corrosion, pits can form and they can again reduce the fatigue strength. Hydrogen embrittlement. This is where the hydrogen can stuck inside the material during manufacturing. The hydrogen can come from air or moisture during the manufacturing operations. And galvanizing or electroplating. These are, we're gonna later learn, surface treatment operations that can introduce some surface roughness and that can reduce the fatigue strength. So residual stresses, throughout the class we will talk about these when we are talking about manufacturing processes. And when we shape a part, basically, even if we remove all external forces, there is going to be stresses remain inside the material. Okay, so first seeing in at A we are seeing a part that is under bending. And under bending, this bar, of course, there is a distribution of tensile and compressive stresses that are forming. At some point, these bending stresses will reach to a point the material is now experiencing yielding, and the stress distribution will look like this. Now, once you remove those bending forces, bending moments, now what is it going to happen here is the forces will act on this in opposite directions once we remove the bending stresses. Okay, so at the end, the net stress distribution will look like this. That is going to remain in the sample. So if we remove with machining, let's say we remove the part of the material from the surface, this will disturb the equilibrium of these residual stresses, and therefore the bar has to acquire a new radius of curvature because of these internal forces, and such disturbances of the residual stress cause warping of parts. And these are shown in the next slide. So again we are seeing in this after we machine, because there are residual stresses after we machine or cut, how the parts will gonna look like, and this is because of there are residual stresses. Okay, the residual stresses can also form due to temperature gradients along the part, because let's say you are doing casting, hot forging, and some parts of the part is much warmer compared to the other parts, and there will be expansions, contractions differently along the sample, and this will create stresses in between the different regions of the parts, and this will again can create residual stress inside the material. Okay, so these residual stresses are important in explaining different behavior, different observations that we are seeing. Again, a tensile residual stress is very undesirable because, as we talk, it can lower the fatigue life and fracture of the parts. Because you already have a tensile stress inside the material, and it is gonna be difficult for the part to handle external forces, external tensile stresses. Therefore, usually to compensate that, compressive stresses are introduced to the surface. Usually that is with a technique called shot peening or surface rolling. And we're gonna see these. Alright guys, so in this chapter we basically learned that manufacturing techniques will cause plastic deformation in the material that we are trying to shape, and it is important to determine mechanical properties because we need to determine what type of processing parameters are necessary to manufacture that part. And tensile test is gonna give us a lot of information in terms of the mechanical properties of the materials. And compression tests, we said, not very reliable, and torsion tests can be performed if the part is going to be exposed to shear stresses. And for brittle materials, bending and or flexure testing is available. And hardness is a property that is related to the strength of the material and wear resistance of the material. Fatigue tests are giving us endurance limit, and creep is a permanent elongation under static loading for a period of time. Impact tests are giving us the energy required to break down a sample. And failure and fracture is important in manufacturing operations, and characterizing the fracture morphology is important in understanding why actually the material failed. And we need to understand when we work on the sample when it is exposed to different temperature gradients, there can be residual stresses in the sample, and these stresses can cause material. If we work on the material, cut some parts of it, there will be unhomogeneous distribution of the stresses, and the material will basically when we cut it, like it's gonna bend in certain regions. Okay, so you guys gonna be assigned homework 2 now, and in Canvas, don't forget to do that, okay?